Okay, so good day everyone. So last meeting, we started our discussion on collisions and we learned that there are two types of collisions and we already solved an example on elastic collision. So we have learned that elastic collisions are those collisions in which momentum and kinetic energy is conserved. So supposing we have particles A and B colliding with each other. So we have A particle A colliding with particle B. So we have particle A moving towards the right. Okay, we have particle A moving towards the right. And then we have particle B mo moving towards the left. So they undergo a head-on collision, wherein after the collision, particle A goes back to the left and particle B goes back to the right. So before and after the collision, the total momentum and the kinetic energy is conserved. So supposing for particle A, the mass of particle A is ma, and the mass of particle B is m sub b. And then before the collision, we have the velocity of particle A as va, and the velocity of particle B as vb. And then after the collision, the velocity of particle A is VA prime, and the velocity of particle B is VB prime. So the total momentum before the collision is equal to the total momentum after the collision. So the momentum of particle A before the collision is MAVA plus the momentum of particle B before the collision MBVB is equal to the momentum of particle A after the collision MAVA prime plus the momentum of particle B after the collision MBVB prime. Also, the total kinetic energy is conserved. So the total kinetic energy before the collision is equal to the total kinetic energy of the two particles after the collision. So kinetic energy of particle A plus kinetic energy of particle B is equal to the kinetic energy of particle A plus the kinetic energy of particle B after the collision. They're equal. So 1/2 MAVA squared plus 1/2 MBVB squared equals 1/2 MAVA prime squared plus 1/2 MBVB prime squared. And then we were able to derive an equation showing us the relationship of the velocities of the two particles before and after the collision using these two equations. And also we solved an example of a head-on collision, head-on elastic collision along a straight line. Now, I also gave you an assignment of a collision wherein it's already two-dimensional. So if two-dimensional gani siya, di ba, we consider na the x and the y-axis. So for example, we solve this problem. There are two balls which are colliding on a frictionless surface. So ball A has a mass of 20 kilograms, initially moving at 2 meters per second, parallel to the x-axis. And it collides with ball B, which has a mass of 12 kilograms, which is initially at rest. So after the collision, ball A moves at 1 meter per second in a direction that makes an angle of 60 degrees with its initial direction. So, okay, instead of 60 degrees, let's say this is 30 degrees with its initial direction. So what is the final velocity of ball B? Okay, so first and foremost, we have to draw the figure. So we have ball A. We have ball A, which has a mass of 20 kilograms, moving at a speed of 2 meters per second parallel to the x-axis. So let's say, for example, it's moving towards the right. Okay. The velocity of A before the collision is 2 meters per second. So it's parallel to the x-axis, meaning it's horizontal. The mass of ball A is equal to 20 kilograms. And it collides with ball B. It collides with ball B, which has a mass of 12 kilograms, and it's initially at rest. So V sub B equals 0 meters per second. After the collision, ball A moves at 1 meter per second in a direction that makes an angle of 30 degrees. Okay, again, it's 30 degrees with its initial direction. So if this is our reference line, this is our reference line. Okay, diba? This is the x-axis. So the direction now of ball A would be, okay, this is now after the collision. Ball A is already here. And ni-form na siya og angle nga. So nalagbot siya padung diri. Ball A is already here, making an angle of 30 degrees, no, with its initial direction. So what is the final velocity of ball B? So the meaning of the question here would be, what is the, of course, the magnitude, no, of the velocity or the speed of ball B and the direction. So let's make an assumption that ball B is here after the, so by the way, si ball A will have VA prime of 1 meter per second magnitude at a direction of 30 degrees, no, north of east, or 30 degrees no, above the horizontal. So for ball B, we don't know the angle it forms with the horizontal. So let's say, for example, it is an angle theta. And we also don't know the magnitude of its velocity. So because this is already two-dimensional, we consider now the x and the y component. So the momentum conservation equations will be considering no duha na kabuok ka component. So again, it's the x and the y component. So along the x, direction, meaning we are talking about the horizontal component. Okay, so MA, VA along the x. So this is before, because momentum is conserved, MB, VB along the x is equal to MA, VA prime along the x plus MB, VB prime along the x. Right? So what is 0 here? What would be 0 here? Now, in this case, again, we are looking for VB prime no, along the x. So if we'll just, manipulate the equation, so MB, VB prime along the x, so this one is equal to MA times M, or that's V rather, VA along the x plus MB, VB along the x minus MA, VA prime, VA along the x prime. So VB prime along the x is equal to MA, VA along the x, okay, plus MB, VB along the x minus MA, VA prime, or VA along the x prime over MB. All right? Now, remember, VA prime has x and y components. So this is VA prime along the y, and there is VA prime along the x. Now, this x component of VA prime, di ba, is equal to VA prime cosine of this angle 30 degrees. And our VA prime, or VA prime along the y, is VA prime sine of 30 degrees. So this VA prime x or VAX prime can be substituted using VA prime cosine 30 degrees. And also, we can cancel out MBVB prime, VBX rather, because that is the initial velocity of ball B is 0 because it is initially at rest. So VB prime along the x is equal to the mass of ball A, which is 20 kilograms. Along the x-axis, VA is 2 meters per second, okay, minus the mass of A is 20 kilograms, okay, and then VA prime cosine 30 degrees. So what is VA prime cosine 30 degrees? So VA prime, or the velocity of ball A after the collision, is 1 meter per second and times cosine of 30 degrees. Okay, times cosine of 30 degrees divided by the mass of ball B, which is 12 kilograms. Okay, so we have the x component of VB prime after, or VB after the collision. So using your calculator, that's 20 times 2 minus 20 cosine of 30 divided by 12. So for an exact value, you will get 20 minus 5 square root of 3 over 6, no? Meters per second, or that is approximately, if we're gonna round it off to the fourth decimal place, that's 1 point, it's just 1.89. Okay, 1.89 meters per second. Okay, so that is the x component of the final velocity of ball B. Now let's go to the y direction. So along the y direction. Okay, along the y direction or along the vertical. So MA VAY plus MB VBY equals MA VA prime Y plus MB VB prime Y. But since ball A is just moving along the horizontal initially, so we can make MAVAY 0. And because ball B is initially at rest, then MBVBY is also 0. So therefore, the component y of the final velocity is equal to negative MAVAY prime VA prime y over m sub b. So negative, the mass of ball A is 20 kilograms, and then its y component of ball B is VA prime sine 30 degrees. Or what is VA prime? That's 1 meter per second times sine of 30 degrees divided by the mass of ball B, which is 12 kilograms. So the y component of ball B is equal to So that is negative 20. That is sine of 30 degrees divided by 12. It will give us negative 5 over 6 meter per second. So it's telling us na positive man ang VBX o negative man ang VBY. So, diba, if this is our Cartesian plane, okay, so for the ball B, positive si X. Okay, so this is VB prime X here along the Y, and the negative, no? Si VB prime along the Y. So meaning it is at quadrant number 4. So these are still the X and the Y component. So we still have to find the resultant vector to find VB prime. So solving for VB prime, which is the resultant now of VBX, VB prime X and VBY prime. So VB prime is equal to the square root of VB prime X squared plus VB prime Y squared. So that is equal to the square root of 1.89 meters per second quantity squared plus negative 5 over 6 meters per second quantity squared. So our VB prime is the magnitude of our VB prime, that's the square root of your VB prime X quantity squared plus the square root of your VB prime Y quantity squared. And our answer is, if we round that off to the fourth decimal place, it's 2.0655 meters per second. So that is the magnitude. But we have to solve for the direction. So solving for the direction. So the variable that we use in our figure here is theta. Okay, so theta therefore, di ba, sa ato ang drawing ana. So mo ni siya ato ang VB prime. So naa si theta dire. So di ba mo form siya og triangle. So this is VB prime, this is VB prime Y, and this is VB prime X. Okay, pardon the drawing. Let's make that drawing ko. So this is VB prime. Yan, muna siya si VB prime along the X. And this is VB prime along the Y. And this is our angle theta here. So therefore, theta is equal to the arctangent, okay, arctangent of VB prime Y over VB prime X. So theta is arctangent of 20 minus 5 square root of 3 over 6 meters per second divided by negative 5 over 6 meters per second. So theta is equal to, using your calculator, is theta equal to, I'm sorry, baliktad. It should be 5 over 6 rather. Okay, it should be negative 5 over 6 over 20 minus 5 square root of 3 over 6. So our angle is, so in your calculator, you will be able to get a negative value, no, but we're taking the absolute value manana. So you will get 23.7940 degrees. So again, because the x component is positive and the y component is negative, so it's located at the kanang y-axis. Or pwede ra sad nga maingon ka nga, you can just say the velocity of ball B is 2.0655 meters per second. Yeah, at an angle 23.7940 degrees below the positive x direction. Okay, so that's how you solve if gani two-dimensional na ang elastic nga collision. Okay, now let us proceed to the inelastic collision. So inelastic collisions. So again, for inelastic collisions, what will happen? For inelastic collisions, we have momentum. Momentum is conserved. Okay, kinetic energy is not conserved. Meaning, total momentum before collision is still equal to the total momentum after the collision, but kinetic energy before the collision, total kinetic energy, before the collision is equal to the total kinetic energy after the collision plus, pa siya yung mga plus, no? Like energy which has been converted to like heat or other forms of energy. So, pwede thermal. So, thermal or maybe potential. Okay, so thermal and other forms of energy. Okay, so that's for an inelastic collision. So, for example, we have, diba, we solved kadtong railroad track in the discussion, and then they were stuck together after the collision. So by the way, that is also an example of an elastic collision, but that is a special case that is called a perfectly inelastic collision. So in a perfectly inelastic collision, while momentum is conserved, kinetic energy is not conserved, but the two objects stick together. Okay, two objects stick together after the collision. So what does it mean when they stick together after the collision? Okay, therefore, the two objects share the same velocity. Of course, that is after the collision. Okay, so like for the railroad track, just the two trucks that were colliding head on. Let's just solve another problem. Yeah, it's here. So, diba, there was a railroad car, okay, car A, which has a mass of 10,000 kilograms. We solved this problem. And it was traveling at a speed of 24 meters per second. And it strikes an identical car B, which is also um, not 1,000, but it's 10,000. So 10,000 kilogram car B, which was at rest. Okay. And then the cars locked together as a result of the collision. And we were looking for the common speed that they experienced afterward. So if we are going to compare, no, if we are going to compare the kinetic energies of the two particles, no, how much we're asked this time, how much of the initial kinetic energy is transformed to thermal or other forms of energy? There must be a discrepancy. So, total kinetic energy before the collision equals the total kinetic energy after the collision plus other forms of energy. So let's say for example we use the variable delta E to represent all the other forms of energy. So before the collision, we have 1/2 ma VA squared plus 1/2 mb VB squared equals 1/2 ma VA prime squared plus 1/2 mb VB prime squared plus delta E. And this is 0 for B because the particle B was at rest. No? And then, so you just substitute the values. We have 1/2 times 10,000 kilograms, and then the velocity of particle A was 24 meters per second quantity squared. That is equal to 1/2. We can just, diba, because the velocity here after the collision for VA and VB, they're equal. So if you just put an arrow here, this would be 1/2 ma VA squared equals 1/2, and then we can just factor out, no, na V prime, that is the shared na velocity after the collision, times ma plus VA prime squared rather, times ma plus mb. Diba? I-factor out na to ang 1/2 og ang velocity nila plus delta E. So 1/2, the shared velocity that we were able to solve last time was, so after the collision, so V prime, which is equal to VA prime, which is equal to VB prime, is equal to, that was 12 meters per second. So 1/2 times 12 meters per second quantity squared, and then we have the shared velocity now of the sum of the two masses, which is 20,000 kilograms plus delta E. So delta E is equal to 1/2 times 10,000 kilograms times 24 meters per second quantity squared minus 1/2 times 12 meters per second quantity squared times 20,000 kilograms. And the energy that was transformed to the other forms of energy is therefore equal to, calculator. Okay, so that's 1,1,440,000. This is energy G, so that is joules. Or you can just write that as 1.44 times 10 to the power of 6 joules, or you can write that as 1.44 megajoules. So this is the energy that was transformed to other forms of energy. Okay, so let's solve another problem for inelastic collisions. Let's try